Very good evening, everyone. I am Engineer Suran Fernando, Chairman of the National Engineering Heritage Forum of IESL, and it's my pleasure to warmly welcome you to the second public webinar organized by National Engineering Heritage Forum of IESL. Today, we turn our focus to Sri Lanka's ancient waterworks, remarkable engineering feats that showcase the skills and foresight of our ancestors. From 6th century BC to the 12th century AD, the island saw an extraordinary development in water management, featuring advanced and sustainable hydraulic systems. These engineering achievements, ranging from small-scale work to grand irrigation schemes, were carefully designed to work in harmony with the environment and support socio-economical needs. While modern technology continues to shape the contemporary water management, a closer look at historical records shows that our ancestors used strategic principles that ensured long-term sustainability. This presentation aims to explore those fundamental principles, drawing insights that remain highly relevant today. To guide us through this fascinating subject, we are privileged to have our speaker, a highly recognized expert in the field, Engineer Bhadra Kamaladasa. Engineer Bhadra Kamaladasa began her career as an irrigation engineer in 1978 and retired in 2015 as the Director General of Irrigation. Throughout her career, she traveled extensively across Sri Lanka, overseeing construction, rehabilitation, operation, and maintenance of irrigation schemes. Her deep involvement in these projects gave her invaluable insights into the country's ancient water management systems. Driven by a passion for understanding the past, she had dedicated herself for researching, compiling, and analyzing ancient water management techniques, compared them with modern practices through the lens of contemporary engineering theories. It is an honor to have her with us today. Without further ado, let me invite Madam Bhadra Kamaladasa to deliver the webinar. Over to you, Madam Kamaladasa.
Thank you very much, Suran. Good evening to all of you. Thank you very much for the introduction and also organizing this webinar, even though it is with a short notice. So for the benefit of having clear connection, I will switch off my video. I hope it will be okay. And then to start with, how did ancient engineers without modern tools constructed reservoirs, barrages, and transbasin canals that withstood centuries? What are the lessons we can draw from these unique designs? That is what Suran also explained. My presentation explores these fascinating insights, focused mainly on large and medium schemes. So I might spend about 45 minutes to 50 minutes on this, and then let us have a Q&A session after that. This presentation brings highlights of an ancient technologies, compares with modern practices, underlining their strengths and weaknesses for today's engineers. So I will touch briefly the listed topics to arouse your interest for the future studies. I'm sure within this short time, I can't go details of each and every aspect I am going to touch, but hopefully I can make aware of the areas where people can pick up from that point onwards and go forward. Let us go from the basics. Irrigation projects actually require long-term vision to conceptualize, often spanning decades. From the time of the initial project idea that is proposed up, maybe coming up from the field itself, from the farmers or water required other beneficiaries or national planners. Up until the commissioning, it will go through these stages as shown in the flow chart. Depending on the availability of laborers, materials, funds, and also depending on the policies of the government, sometimes this will take more than the time indicated. So you can see minimum, at least minimum of 10 years will be needed for commissioning of a new scheme at the ground, and it will go beyond that depending on this the above facts I just noted. So it is at the same time, it is not a one-man show as we often hear in folk tales. This man built up this reservoir and things like that. Actually, it is the success of both ancient and modern projects depend on the experience and dedication of multidisciplinary team. That we should keep it in mind that it is a teamwork actually. So again, basic information for you to keep in mind while listening to this presentation, because I will come back to this information from time to time, remind you the basic information necessary for planning and design of a reservoir projects are shown in this diagram, the basic things I might say. So you might find how much professional efforts need to go in with technological tools. Of course, I have mentioned few here, the tools. If the project scope expands with diversion canals or any other requirements, depending on the water availability or water requirement, or having the site-specific issues, this list too will be also expanded. Then, since I discuss more matters on reservoirs, I thought of introducing basic features of a reservoir project for the benefit of the audience here who are not familiar much with the principal features of a reservoir project. This is a typical layout plan of a simple scheme. It consists of a dam, construct across a river, spillway, sluices, and canals. Then while this seems a very simple arrangement, ancient engineers optimized these features based on site-specific needs, deviated wherever necessary, depending on the specific site conditions. I will go through some components of this list for you to get general idea about planning and design principles in foregone era and also in contemporary era. Then the basic consideration the design engineer will focus on dam will be, first and foremost, the dam should be stable. That is obvious. Then it should be able to control excessive seepage, only allowable limit be there through the dam, especially the earth dam. For that, suitable materials to be used and construction to be done with extra care, having very strict quality control. The most frequent damage occur to earth dam is covering the slope that needs to be prevented in the upstream due to the wave action where the riprap is used. So those are the very basic things I must mention here. The current recommended section for a dam is shown in the figure here. Typically, the upstream slope is on 1 on 3, while the downstream side is more steeper, having 1 on 2 or 1 on 2.5 to ensure the stability. So you may notice that the ancient Nachaduva a dam shown in this right-hand side picture also followed almost a similar design section. In some ancient dams, we could notice over-designed sections anyway, having flatter slopes and having bigger crest vents and a bigger section than this. But today, engineers optimize designs mainly considering the overall costs and also to save the raw materials. One other safety factor in the ancient earth dam is the high freeboard. That means height difference between the spill crest and the dam top. This space is allowed to retain flood water during the storms, as mechanical gates were not available in ancient era. Flood control was possible only through natural spills. So the sketch in the sketch shows the Kalava ban based on the surveys done on restoring during the 1870s, and the photograph also is a Kalava sluice that was not raised according to the new design. Anyway, this volume of water at the between the dam crest and the full supply level, spill level, what I have marked here is can be called as inactive volume, because it is a flood detention volume, and it will go away, I mean, with the when the flood recedes after the storms. So as the freeboard was, I will go into the current section as well here to show you the difference. Actually, in the ancient Kalava dam, the freeboard was 3 meters minimum. It was in some places it was more than that. Then with the new design of new hydrological analysis, this could be reduced to 1.5. And now with the introduction of the radial gates, and also by extending the spillway length, and with all these things, we could reduce the freeboard here, and also increase the active storage, and also increase the height of the sluice. So you can see this new sluice in Kalava that is at the same level of the Ban crest level, and you can see the volume of the active storage that can be used for various benefits could be increased on that way. The above phenomenon can be is explained here comparing the ancient Kantale dam as well, and also the current dam. You can see in the table the original reservoir capacity was very low. Now I have shown here the the spill level, ancient spill level of Kantale dam, and also the Kantale dam crest here. So the freeboard was about 25 feet, and we could in 1950s, that is after restoring the ancient dam, ancient reservoir, the capacity was 35,000. But with the introduction of, with the raising the freeboard with various interventions, we could increase it to 114,000 acre feet by now. And I'm sure you would have got the basics behind the freeboard, what is allowed and what can be allowed under current situation. One other interesting fact about the material used for dam construction, I'm sure if quality control engineers are here, you know how much effort are to be taken to select suitable raw materials for a dam. We currently use the universal soil classification to select best material for different zones. This is the universal soil, one of the universal actually soil classification diagram I selected from USBR publication. It gives a clear idea for the engineer to select the characteristic of soil material that is suitable for a dam. And then you can see in the Samantha Samanta Pasadika, that is a 5th century chronicle, and Sika Valanda Ha Sika Valanda Vinisa. I'm not sure whether I pronounced the words clearly. Those are that is the 10th century document. So those documentaries, those books reveal some of the soil properties that were recommended by the ancient planners for their, the dam construction during that time. Sorry, I have given detail of the details, lengthy details which I quoted from one of the documents I referred. So I'm not going through the details. Anyway, just to compare how these soil collections, soil selection was done in ancient era as well as by the current engineers. So the reprep is an important feature that need in Earth dam, as I mentioned earlier. It is needed for long-term sustainability when when we were going to restore many large dams. Modern engineers found that riprap were intact even after centuries of abandonment of the beach dam. In modern dam design theories, design of a riprap follows up with serious design calculations to determine the size of the boulders and thickness of the riprap layer and all these things. You can see the riprap place in Senanayaka Samudra. Actually, this photograph was taken about 5 years back. And you notice that all the riprap that was placed after rigorous calculations were displaced during the last 7 decades, and but still the Giritale riprap, which was dressed stone masonry that stood 14 centuries, and it is still being used. So what miracle made this happen? That is a question we are having in mind. Then I thought of sharing the design details of another marvelous riprap design found in Kudavidachya, which is still in abandoned state, and education department is going to restore when the funds received. The special feature in this design is placing the riprap at 2 levels. You can see in this cross section, those were there were two ripraps in 2 levels, and having exposed earth dam, you can see the a berm in between these 2 layers, and I must say there is no scientific explanation yet to this design. How it survived without displacing amidst of exposure to several centuries of storm, and it is, I'm sure most of you know, that is in the middle of the Wilpattu National Park. So crossing path of the elephants. With all these disturbances, still it is been there without any disturbance. So you can see the sizes of the boulders. I like to call them nicely cut stones, actually, not the boulders. These are shown in this figure in the right-hand bottom side. No binding materials have been used, but with their self-weight and balancing each other, anchoring to the slope, the whole system remains stable. The another aspect I want to bring to your attention is the gradual development. The ancient engineers actually constructed reservoirs by gradual expansion. So an approach modern planners should consider for a long-term adaptability. This is a very nice theory that we can follow. It is like a sorry. it is like a building a house to suit your budget first, and then take the extensions while your family requirements expand. Likewise, you can see the ancient Kalaivavar has not been created as a single large reservoir, but a combination of two large reservoirs. The Balaluvavar was constructed in 1st century BC, and the next adjoining Kalaivavar has been constructed across Kalawaya in 4th century AD. So by combining these two, King Dhatusena created the Kala Balaluvavar. The most amazing intervention here is aligning the access of two dams to create a single dam at a later stage. So I'm sure that is the most amazing point here I want to bring. What if the alignment did not tally when the efforts of combining two dams were tried? So I leave that question for you to think over and find the answer. Another impressive example is Parakrama Samudra. 7 reservoirs are believed to be connected to form Samudraya. Topawa has been built during 4th century AD, while Parakrama Vavar was built in 12th century. When the topographic surveys were done in early 1900, the surveys found that there is a feeder canal starting from Ambanganga is extended northern direction. You can see it is extended the northern direction for a long stretch, feeding each and every of these individual reservoirs. Anyway, by that time, they have not identified these reservoirs. Only the Topa was in existence, and they thought it is only the feeder canal is going up to the Topa River. Then while restoring in 1950s, only 3 reservoirs were restored. Dumutuluvavar, Parakram Samudra, and Topawa, and later Kalhagala was restored. Still, Buvavar is not now. It is not possible to restore at the moment. So likewise, this is a combination of few reservoirs here. To support this phenomenon, you actually I must go back to the this slide again. The beauty of this complex is that each of these reservoirs can operate independently. As separate sluices are there, there is a very successful strategy for current design engineers to follow to optimize the water resources in the system. Actually, in Mahavansha, it is mentioned that there were about 20 sluices with canals starting from Parakrama Samudra. So that may be the reason why each maybe a large reservoir would have had 3 or 4 sluices. Likewise, that may be the way many canals, the sluices are mentioned there. Then the another typical another example I want to quote here is the Miyoya. In Miyoya, you can see the 5 reservoirs are located in a similar manner, but only 3 reservoirs are interconnected. Those are not connected like Parakrama Samudra, but operate separately. Attaragallava, Palukadavala, and Ambakolavala. They are interconnected anyway with a feeder canal. So similarly in Kantale, when you see the topo map here, you can see I can say 5 reservoirs are located in a very similar manner. Anyway, Kantale and Vendrason reservoirs are interconnected now, and Paravi Panchan and Galmatiava are operated separately. But there is a belief that the Vendrason tank and Paravi Panchan reservoirs were interconnected in ancient era. Then let us see how the ancient engineers handle difficult terrains. That is another important area. When selecting a location for a dam, I explained the advanced technologies used by modern engineers for hydrological analysis, geological investigations, and also in surveys when fixing the dam axis across the river. Ancient texts like Samantha Pasadika describes how geological conditions were scrutinized, resembling modern geophysical investigations and emphasizing site suitability. Actually, this is Wahalkada bed survey that was done in mid-1960s during restoration of Wahalkada. Original construction was recorded as 3rd century BC when the restoration was done in 1960s. So when I went through this drawing, I could not believe the exemplary decisions made by ancient engineers in orienting and selecting the main dam and the several dams. What you can see here as dam 2 and 3. Actually, unless one has a very accurate contour survey, you cannot identify exactly where these additional dams to be constructed on the reservoir rim. The main river, you can see the main river crosses through a very narrow valley where the main dam is located. It is a very small dam. When someone go to the site, you can see it even very small dam built across the close in the river. But the two ancient sluices were located in dam 2. That is not the main dam again. It is in a saddle dam in the terminology what we are using. So I'm sure this would have been done based on the results of precise leveling, and one can decide the locations of sluices that can deliver the water to the service area by only following up a very accurate leveling. Then Sorobora Weber is also located at a very unconventional location. I'm sure modern engineers would be reluctant to select this as a dam suitable location for them because due to the extensive rock outcrop. Uh, uh, that is usually that rock will create, I mean, interface of the rock and the dam will create seepage paths, making the piping or seepage failure. So we used to avoid this type of places wherever possible. But these ancient engineers have taken that bold decision to build a dam here. Sorobora, and I must mention here that Sorobora is one of the reservoirs that has not been breached even during the dark era of our history. It was so solid. I can quote many more examples anyway, but selected this one. Irattaperiyakulam medium reservoir in Vaunia. The terrain here too is extensively covered with rock outcrops, and this layout plan shows, you can see the layout plan here. It shows the bund is a combination of 4 rock outcrops and 3 small earth dams that connect the rocks to form a reservoir. So I'm sure you would have got some idea of the selection of the hard, I mean, difficult terrains without any hesitation, how they have gone into that level. So another example I want to highlight about difficult terrains is a giant stand. It is located in a very peculiar location in Mana, what is called as rice bowl of the country once. The current engineers are also puzzled over many aspects associated with this one because it is located in a small sub-basin. It is not located in a river basin. It is adjoining to the Malwatu river basin, where actually the catchment in this section is a very limited. So the inflow to the river is very limited. There is no river crossing the dam except some drainage paths. And also the geology of the area is not much suitable for a storage reservoir. Seepage is possible, and foundation is not very conducive. So despite all these negatives, a shallow reservoir has been formed with a U-shaped embankment. The total irrigable area is 4,350 hectares, and the about 162 small reservoirs in downstream of the reservoir get filled up during the Maha season to feed the irrigable area under them. But during the water shortage time, that is in Yala, small reservoir beds convert to irrigable area and get water from the main canals. So I must say I cannot find reference to a similar design anywhere in the world, and definitely this would have been the designed by a group of genius people in our country. Another unusual design of dams in ancient Sri Lanka is locating the dam not across the river. I mentioned at the beginning when introducing, the dam is usually built across the river, but this in most of the you can find many rivers, ancient reservoirs in Sri Lanka are not built across the river. Maybe due to I will briefly explain the reasons. It is built parallel to the river. Out of many examples, I like to quote the Rugam in Batiklo. The strategy was to divert water to the reservoir from the main river, right? This is the main river going, and there is an anecut. This is the dam construct parallel to the river, and then there is an anecut in the upstream. Then water will be diverted to the reservoir whenever necessary, and then there is a sluice at the LBN that will release water again to the river, and have the water will be controlled through the sluice and released to the river to pick up from the anecut downstream. So I'm sure you would have got some idea about peculiar situations, special situations where decisions have been made, unconventional designs that were followed by our engineers. The next component I want to highlight is the spill. In an irrigation reservoir, it is a very important feature. To decide the location, actually the geological experts' input is necessary, while the hydrological expert can only decide the type of the spill and the capacity. And design is to be supported by historical data at the site, at least 30-year rainfall data and river flow data, and statistical analysis has to be followed up. So the characteristic of the spill should be it should be able to control outflow during the flooding, and releases should not damage lives and property downstream, and no overflows to be allowed that could create damage to the dam. Again, here in Samantapasadika, it has mentioned about the spill as a mechanism to control outflow with a permanent spill or section suitable to breach during floods. So the same principles, the breaching section and also selection of the spill and things like that are there in our current guidelines used by our engineers. According to the current dam safety theories, the earth embankment, actually earth dams are vulnerable for many types of failures. You can see the type of failure. Few failures I have given the figures here. According to the global statistics, the most common failure mechanism is a hydraulic failure that happens during stormy weather conditions by overtopping, as shown in this diagram, by overtopping the dam. So, if the dam foundation or dam itself is comprised of bad qualities of soil, this type of failure, piping or seepage failure, can occur. And this is the structural failure that can happen when if the sluice tower or sluice barrel has developed some problems, or if there are leakages through these components. Those are the basic facts you have to keep in mind when going through the stability of the dam and sustainability. So when studying the history of failures of the Sri Lankan dams, it is noted that majority of the dams had been failed due to overtopping. That is hydraulic failure, as I explained in my previous slide. So this layout plan of the breached Hurulava drawing prepared during restoration in 1950s, in 1950s, show the dam has been breached at the river crossing. You can see the dam breach, the longitudinal section here of the Hurulava dam shows that the breach has been occurred at the river closer. So it is though it is not a sluice failure anyway. That is not a structural failure. As I mentioned, most of the ancient dams were failed due to the hydraulic failures. The sites selected for spillways were perfect, I must say, when carefully study the details of ancient spillways. So the ancient geotechnical engineers have done their part perfectly. Yeah, this is only one example, Nachaduva, where most suitable location had been selected for the spill. Yeah, one of the main concerns of the planning engineer of the current era, two is a suitable place for a spill, and then can which can safely pass the flood volume without damaging the dam or downstream system. That is very important decision the planning and design engineer should take. When talking about control of flood discharge, we find more peculiar system again adopted by ancient engineers. The Debarwewa, Tisava and Yodawewa system in Tissamarama. That is a very rare example of multi-stage flood retention system. Flood flow from Debarwewa is directed to Tissawewa, and then from Tissawewa to it flows to Yodawewa. From Yodawewa only the flood water will direct to the river to flow into the sea. Operating of such a system requires precise coordination. Not only now, actually, previously it would have been a very difficult operation. So this again is a very risky design, I must say. When restoring the system anyway in early 1900s, the same system of flood management was followed. I'm sure those if there are engineers here, those who operate the current system know how much effort is needed to balance the three reservoirs during the floods to safeguard the infrastructure and also the properties downstream. I must note here that in any of the newly designed reservoirs, this type of complicated arrangements are not adopted by current planners. I'm sure we will ensure that to provide separate spillways to each and every reservoir. As mentioned earlier, most of our ancient dams have been subjected to hydraulic failures due to the insufficient spill capacity. The Kalawa is a very good example for that. While doing the hydrological analysis using the current scientific approach, the current engineers found that the spill length and length had to be increased. at the double fold, in addition to the extending the spill length. So the current Kalababa spill is more than double, maybe double fold, I mean, than the previous ancient spill, and also incorporates 2 radial gates. I'm sure most of you had noticed that. So this table shows the original spill lengths and new spill lengths provided after calculating the flood flow under modern hydrological theories. That is, during the restoration, these were adapted, and the table, I got this information from hydrological analysis and analysis done by engineer B.T. Dharmasena. So you can have a comparison, comparative analysis, the length of the ancient spillway, and also the new spillway length, and also the additions what have been added to the spillway later. Another aspect I want to bring to your notice during this presentation is in-basin diversions. That is very effective and genius design I want to mention. Design method adopted by our ancestors in water management. So ancient engineers mastered in-basin diversions to ensure the water availability year-round. Such techniques offer valuable insights actually as a climate resilient water management, what we are talking very frequently today. So I can quote many examples all over the country for in-basin diversions, but take only a few examples to explain the theory behind it. This is Tabbo Reservoir located across Nanneria Oya, a tributary of Mioya. To serve the acreage in Tabbo area, inflow in this stream, inflow from the Nun area was not sufficient. So what ancient engineers have done is they have diverted water from main Mioya by constructing anicut in across the Mioya, and then divert the water to non-area. It is since it is a single basin one, we call it a in-basin one, in-basin diversion. So Tabova, it is a very successful and effective, not only during water shortage period, but also during the during the floods as well. The second example, again, I want to quote Parakram Samudra, because it is the in-basin diversion here again happening. The in the it is the Angamadil Anicut diverts water through a Yodala called Akasaganga from Amanganga. And the advantage of in-basin diversion here again is that option of available, shutting down the Yodala water diversion during the flooding. So if when we don't want water to flow into the Parakrama Samudra during the flood time, we can close the Angamadil Anicut and allow the water to flow in the Ambangaga without adding to the Parakrama Samudra. Actually, the inflow in the Parakrama Samudra from its own catchment is controlled by 10 number of radial gates. I'm sure most of you had seen it through the media that was shown 1 or 2 months back. Even after closing the Angamadil Anicut, sometimes we may have to operate the 10 radial gates. That means the inflow from the own catchment is so high. But during the drought period, definitely the water in-basin diversion is necessary for the Parakram Samudra irrigable area to feed with. Okay, I have shown here the water flow from Angamadil Anicut. Then another A point I want to highlight here is another solution for inadequate spillways. To address the inadequacies of spillways, ancient engineers have found another method of detention of water coming from, from its own catchment. This methodology was used to control the inflow to the reservoir, and it retards. You can see, I am sure you can see this picture clearly. Sorry about the quality anyway. You can see all these in, small streams that coming into the reservoir were blocked by small reservoirs as these were called as flood detention reservoirs, and it will control to some extent during the flood period in overcoming the overtopping of the dam. It is another actually in current design principles also we use this type of approaches. We cannot design the spillways to the level what the design design engineer will expect. The next important aspect I want to cover here is the sluice. This is actually sluice is the most frequently code device invented by our ancient Sri Lankan engineers. Usually, the sluice is expected to be the to able to control the water issues required for water supply or irrigation. While the releaser should not damage the bund, no leakage is allowed through the barrel, as I mentioned earlier, or outer surface. And Samantha Pasadika also again here gives some valuable evidence of sluices in operation, not in a comprehensive manner, but in a very simple manner. It has mentioned some information about sluices. British engineers used the word valve pit anyway because they were not much aware of the word, the terminology of sluice. Only later on they were conversant about it. This type of catasorover that are still in use in shallow village schemes being considered the most primitive type actually. It is used by our ancestors. The vertically stacked cylindrical clay pots, clay pipes are used to control water flow through the sluice. Fortunately, we have still physical evidences of more advanced type of ancient sluices, especially in large reservoirs, as shown in this slide. The Kalawava sluice, built centuries ago, followed by hydraulic principles then, that modern engineers still validate same. That is a true testament, I must say, to ancient engineering wisdom. This plan of the ancient sluice of Kalawava drawn in 1890s, and the sluice is head wall type. That means there is no sluice tower here, and this is another simple type of sluice which had been used in many large reservoirs such as Nuwara and many, especially in Anuradhapura, Rajarata area. When restoring the sluice barrel was intact and there was no need to replace the barrel. So this that indicates the complex hydraulic theories what we use now for designing the current sluice barrel and sluice tower would have been used by our ancestors as well. I cannot miss the famous Madhuru sluice in this presentation as it gives many more clues on advanced design principles. To complete my presentation, this is during the bygone era, the meticulous surveys ensured sluice plates at precise elevation, precise location, as we have heard many times. to enable gravity-fed irrigation. That is a method still fundamental in modern water management, what we used here. The sluice barrel, as you can see here, is not a straight one. The direction of the sluice barrel had been changed to suit the site condition. This is extremely, I must say, this is extremely complicated hydraulic design. The arch type dome here shown in the photograph above, that was used over a sluice barrel is supposed to use as a mechanism to diffuse pressure in sluice barrel. Professor, I must mention here, Professor R.A.L.H. Gunawardena, who conducted many investigations in 1980s when this was invented, has written many papers on this, and he has noted that specially killed bricks have been used, which are similar to modern high quality wire cut bricks. So I must say here again, I have never seen such a design in any textbooks what we have used, or this has not been replicated anywhere else also. Another famous unique sluice can be found in Soroborovo, which is quoted even in our school textbooks. We'll look at this creation in the point of view of a design engineer. Question comes to my mind is what type of creative ideas would have come into the design of this sluice, which perfectly matches with the ground condition. If a conventional type of designer handled this planning of the Soroborovo at that time, it would have been sometimes removing the rock at the site and constructing a typical sluice with the sluice structure, what we have shown earlier sometimes. But fortunately, it was in the hands of a creative group who made wonders through their perceptions. This is a tower type sluice which had been there in Achaduva. You can see in the photo. This is again a common type in many ancient reservoirs. I wonder whether there were there were some type plans or guidelines for the designers at that time to follow to have similar type of these structures as we have today in our institutions. Then we discussed that no leakage to be allowed through the sluice barrel or tower if it is embedded in the bund. Here we can see how much care they have taken to seal the sluice tower and the sluice barrel. More clear pictures of sealing methodology can be now these pictures show the sealing methodology that they have adopted. Actually, these photos were taken when the ancient sluice in Kantale Reservoir was dismantled and removed after the breach of Kantale Dam in 1986. The barrel is made out of dress masonry, which is being covered with a thick brick layer, and the brick layer had been sealed by a gum. So you can see the display that is available at the dam top now. When they dismantle the education department dismantled the ancient sluice barrel, it was part of it was displayed here at the dam, and this is the brick layer covering protecting any seepage coming into the barrel, and also the white plot you can see it is the binding materials again protecting water to come in. Then most of the ancient sluice barrels were in perfect condition even after many decades, many centuries of abandonment. We can observe some thin cement mortar has been used to bind these boulders together in some of the ancient barrels, but we can inspect now. The other amazing feature is the fixing of the sluice sill level. I mentioned it earlier as well. The sluice sill level is very important to match the levels of the downstream irrigable area, because the water should flow in gravity, and irrigable area should be always at the level where to the low level of the sea level. So this is a cross section of the band of Kudavilachi showing the location of sluices. It is not that you can see the sluices are not at the same level. LB sluice is at a higher level, and RB sluice is at the lower level. So that means they have done an extensive survey downstream. It is not only the dam site they would have done the surveys, but including all the area, they would have done the surveys and select the suitable sluice sill level that would be possible to drain out the water. I mean, to convey the water to the irrigable area where it is necessary. Another truly fascinating discovery is the unconventional placement of sluices in ancient reservoirs. Actually, while conventional design dictates sluices, as I showed at the beginning, sluices located within the dam itself, our ancestors often challenge this norm with now you can see this Vakaneri reservoir where the sluice is positioned far away from the main bund. It is located in a saddle bund upstream. That is very unconventional and yet a masterfully planned decision by the planners. So this level of strategic foresight and adaptability, I must comment about these things as a irrigation engineer who involved in lot of planning work, and I cannot imagine how this type of design strategies came into their mind at that age. Barrages is another component I want to bring into the surface in today's presentation. The barrages constructed across major rivers are again an amazing feature that demonstrate the immensely the capabilities of the ancient designer, ancient engineer. This is 5th century Tekkam Manikat that withstands extreme flood forces, and I can highlight how the ancient materials and construction techniques achieved modern level resilience, and the Tekkam Manikat can it withholds about 7,000 meter cube per second at a certain flood event sometimes that flowing through the Malwatoya with the releases of Nachaduva, Norveva, and many other large reservoirs. So you can see the large stone blocks interlocked. Sorry, it is not clearly shown here. The stone blocks, but those are again interlocked, and gaps were filled with some indigenous mortar made out of sand, lime, and bee honey, and also some wood resins, as noticed by the researchers what studies have been done. Earlier, also we spoke about giant tank, but here again I want to bring it at this point as a peculiar system again, because I mentioned that giant tank was located in a small basin, not in Malwatoya, and you can see the barrage that Tekkam Manikat that I shown previously. It was the Tekkam Manikat diverts water to Giant's Tank, and the feeder canal that takes water is about 15 miles long, and slope is 1 inch per 1 mile, while the bed width is 55 at some broader sections, and depth is about 5 feet 6 inches. So LB feeder canal also take water from Tekkamanika to Akathuruppu irrigation system. That is again a very good example of a feeder canal and also Anicut that has been combined to the irrigation system very wisely. Then the next example I want to highlight, bring here is the Alahara Anicut across Amanganga. That is so this is now I want to show the layout of the Anicut. It seems that now you can see they have followed the very advanced design principles, while in the previous slide I showed the remnants of the previous the ancient Anicut, and also this is the new Anicut. In drone views, this photo was provided by one Mr. Kasumbi Silo. I must appreciate mention his name here. So I extracted this information from Alahara layout map prepared in 1887 by British engineers, and also Google Map to compare, to elaborate the layout of that. So you can see the Ambanganga branches into two, and this is Ambanganga, and it branches into two branches. This is main Ambanganga, and this is Kudaganga, what you have called. Now this is Mordhakanga that was constructed in upstream now, and the main river path now in this map also it shows that this is Ambanganga and this is Kudawaya, and this is the high ground that is what we used when we cross the Kudaganga and coming into the main Ambanganga Anicut. By selecting this location, to divert water to the Yodala, this is Alahara Minneri Yodala, what they have done is, first they have constructed an Anicut across Ambanganga to head up water here, and then again to head up water in Kudaganga, another Anicut was built up, so the water can be easily diverted to Kudaganga. So this is another genius, design strategy. They have made use of making use of this water availability in Ambanganga. That is very, I must say, it is very difficult to handle this type of water flows. I mean, very high flows coming during a stormy period. So this type of design is very need some high imagination power. However, they have done it, and we know that Alahara Minneri Ala is functioning very well once it was restored to the original section. And the next item I'm quickly going through the next a few slides only I have. So the transbasin canal. Transbasin canal itself is another topic that has involved a lot of conceptual designs. This Alahara Minneri Yodala starting Alahara, it was a masterpiece, I must say. The principles of ancient irrigation engineering in transbasin canals constructed many river basins crossing from when it traverses Kala to Tisavava. The Yodala crosses many rivers across. So again, it is a very complicated design, I must say. There's no need to emphasize how much it is difficult to align such a canal to convey water, even for a half a kilometer canal. If we align that, we know how much it is difficult to direct the flow within that short period. So let's forget about the 87-kilometer long canal, and it carries about 250 cubic. So that is, I must say, it is a pinnacle of our construction, irrigation or hydraulic engineering construction during that era. When when we go into the, I'm not going into the details of this Al-Haramain area first mile drawing I have shown here to give you the details, but I think that already time has passed. I have passed my time more than what was allowed. Anyway, I will come back if there are if someone is interested on that. And the my conclusion here is, when we go deep into the Sri Lankan ancient irrigation system, we realize it is not it is not just feats of engineering. There were masterful solutions to water management challenges, and that remains even relevant today. Most of the design principles, planning principles, even valid today. So let us draw inspirations from this ingenuity of our ancestors, and create engineering solutions to stand the test of time, just what they have done. Actually, we have not, my opinion is, we have not yet harnessed the full potential of our system in view of earning foreign exchange. That is the most pressing issue we are facing at this moment. So this is the land most suitable, the Sri Lanka, to promote hydraulic heritage tourism and irrigation heritage tourism. With that note, I want to conclude my presentation here. Suran, I am not sure whether I have exceeded the time given to me. Thank you very much for your attention. And we could see only the time part, I must say, of the ancient engineering. So we have to see the major, it is like a iceberg, but you can see only a tiny part. We have to see the larger part underneath. Let us explore that unique heritage in a more scientific manner and show it to the world. With that, I would like to conclude. Thank you so very much for your patience and attention.
Thank you very much, Dr. Bhadra Kamaradas, Madam. So there are questions from the audience. So I will get one by one. Before that, is there anybody from the audience who wish to ask questions other than the typed one dropped in the message box? I saw one. So if not, okay, we will go with the received questions. The first one was from Mr. Uma Ruben. So it is regarding the ancient dam construction, Madam. So he was asking, are there any examples of dam built during the King's region that utilize important materials from other locations instead of native materials to overcome the challenges such as unsuitable soil permeability?
Sorry, Sakura, I have to read again. Let me read the question and get that again. And I must correct, I am not doctor.
Okay.
I'm Engineer Bhadrakamaladas. Okay. I have question I am reading Engineer Ruben's question. I have a question regarding ancient dam construction. Are there any examples of dams built during King's region that utilize imported materials from other locations instead of native materials to overcome challenges such as unsuitable soil permeability? No, I can say I have not come across any. I have not come across any evidences on that. I don't see any reason to import materials, especially for the dam. But maybe for if there were requirements for gates, of course, sometimes they would have bought or special timber, but I am not sure. I can't say exactly. We have not seen. That is my short question, Sakura.
Okay, thank you, madam. So the next one is from Ziva, Mr. Ziva,
Nalaya,
and
yeah.
yes.
Okay, I will read it.
Yes.
Ancient dam axes have been now found to be at the best location to optimize the collection and storage of water. Has anyone done research to understand what kind of implements or instruments would have been used during the ancient time? To my knowledge, no. I have not come across any reference, I mean, research paper or anything mentioning that about the instruments or anything like that. Yeah, that's my question. I reply.
Yes.
Sakura?
And madam, then again, Engineer Umar Ruben has asked about how did the ancient civilization conduct topographical surveys and test soil permeability.
To all these questions, I must say there is no record at all. For the time being, we don't know now. A lot of people are talking about some documents that have been taken by the British rulers or who ruled our country as colonized our country. So if anyone can find those things, I'm sure those will be sometimes it may be there, but nothing at this moment for reference for us to get this information.
And then again, ask Engineer Chandana Kurakula Surya, what is the allowable seepage through the dam?
That is actually theoretically that depends on the type of the dam. I mean, now so in embankment dams that is constructed by with soil, there is a limit given, and also in concrete dam also there is a allowable limit. Sorry, I can't give the exact figures here at this moment. May I leave it to another time, Sakura, to answer that question, or if Chandana can contact me, I can give you figures. I'm sorry, at this moment I don't have the figures with me.
So, madam, we will contact, I think it is Dr. Chandan Kulasuri, so we will contact him later on. Yes.
Thank you.
So, and then Engineer Jeeva Varnakula Surya is asking in construction of Moragahakanda Reservoir, have you studied the impact on the ancient irrigation system?
Yeah, actually, during the construction of Moragahakanda, before construction of Moragahakanda Reservoir, they have done a EIA. So in the EIA, it is a must to do the studies on impact of ancient irrigation system. Not only that, the archaeological study had to be done. So these were done, and I'm sure if you have access to that, or maybe with CEA, the reports should be available.
Yeah. And Madam, another question from Engineer Shiva. Then it is about you have mentioned that one of the reservoirs, there was a way to reintroduce excess water upstream of the river. How was this possible if there were no mechanical pumps to lift the water?
Let me see it. You mentioned that in one of the reservoirs there was a way to reintroduce excess water upstream of the river. How was this possible? No, I did mention. You'd have got a wrong impression. I didn't mention of reintroducing excess water. Siva, can you mention what it was? Or
Engineer Siva, if you are still in the audience, you can talk, I think. So I think, Madam, there was a it is about the dam. You have mentioned that after that excess water can pass through the small rivers. That one.
Maybe Tisamaharama system. Excess water pass through one
reservoir. Yes.
Yeah, actually, it is it is not lifting the water, right? It is through gravity only. The spill water from the river will pass to the Tisaveva, and through the gravity only, Tisaveva water will pass to the Yodaveva. There is no way. I mean, nothing was used to lift the water, spill water.
Yeah, and the other two questions, Madam. Then it is about that in your presentation you have discussed a variety of dams and its components are on large schemes. Then, however, the small level schemes, do you still get different varieties or do most of them follow the typical layout?
Yeah, Sakura, actually, more varieties could be found in village systems, I must say, than the large system, right? In 1930s, Irrigation Department conducted research on village reservoirs that were lying close to the Northern and Mana railway track, that is after a railway disaster. The layout plan, layout patterns, field capacity, and many other features of more than 350 village reservoirs were analyzed. And of course, this research paper is there published in the IESL 1933 annual sessions. Based on the results, then engineers were able to develop Sri Lankan guidelines. So that means what I want to highlight is there are number of varieties, I must say, in small reservoirs, and especially the concept of cascade system. The cascade system is another different variety that was recognized only 5 decades back, right? It was not identified as a different variety earlier. Now, if anybody interested, can refer many materials that what is available in the internet now on cascades. Identify the variety of cascade systems, and I'm sure anybody can get more information on that type. I hope I answered your question. Now, is it clear?
Yeah, madam. Yes. Yes. And then those are the questions I have received from the audience. If there are any more questions, you can raise your hand and then we can give you the chance to talk. Okay, so are there no more questions? So we can conclude the session today. So as I am here as the secretary of the National Engineering Heritage Forum. So I would like to give the vote of thanks. Good evening, everyone. And on behalf of the National Engineering Heritage Forum of IESL, I extend my heartfelt gratitude to our esteemed speaker, Engineer Badra Karmaladasa, Madam, for your insightful presentation on Sri Lanka's hydraulic heritage, actually. So your knowledge has deepened our aspiration of these ancient engineering marvels. So, and special thanks I have to give to the IESL technical team, whose dedication and hard work that ensured our program seamless execution of this webinar, actually, on the online platform today. And about our wonderful audience, I sincerely appreciate your participation and also engagement. And then about more enthusiastic questions, because your enthusiasm reflect the more importance of preserving and studying about our rich hydraulic heritage. And also, as we are going to conclude today, let's take this inspiration and also the decision and continue to explore and protect and promote Sri Lanka's incredible hydraulic heritage. So thank you once again, and we look forward to your participation in future sessions also. And thank you very much. And here, from this point, we will conclude the Good Day session. Good night.
Good night. Thank you.
Thank you.